Hello guys, welcome to our unit on gravitational fields with our first topic on the gravitational fields being Kepler's laws of planetary motion. So let's jump right into it. These are the skeleton notes we're going to go through as we complete these notes. These you'll want to have in your notebook before we begin so that you can concentrate on listening and learning and have a little bit less to write as we actually go through the material. So here we go. Our essential question is, how does an understanding of gravitational fields allow for humans to explore the solar system? Okay, let me pick a color that's going to stand out here. So, Kepler developed 3 laws of planetary motion, and in the textbook it goes into some history about how he came to have those. So I recommend you look back at that. His first law of his 3 laws is that he said planets move in elliptical orbits. Now, prior to this, everyone, including Galileo, insisted that planets must be moving in perfectly circular orbits. And he found the data showed that no, they actually move in elliptical orbits. And an ellipse is a figure like this one. Okay, what defines an ellipse is that if you pick a point on the ellipse, then its total distance from both of these points, called foci, will be the same all the way around. Like this total length of these 2 red lines right here is going to be the same all the way around. So if this planet is sitting here, or this object is sitting here, then the total distance between these, or the total distance, like this line plus this line, add up to the same value all the way around the ellipse. So planets move in elliptical orbits, not circular orbits, but the orbits are nearly circular. This drawing is of a pretty pronounced ellipse, but the actual orbits are more circular than this. They're just not perfect circles. The sun is at one of the 2, let me stick with purple here, one of the 2 foci. All right, each one of these points is a focus. All right, the sun is sitting at one of these, and I'll attempt to draw a yellow sun here. So sitting at one of these foci is the sun. Okay, so that's really the extent of law number 1, which is just that the fact that the planets move in elliptical orbits, not in circular orbits. Okay, Kepler's second law. The second law says a line joining a planet and the sun sweeps out equal areas in equal times. Okay, that one sounds a little weird. Here's what it means graphically. Let's imagine a planet that's moving along this orbit. So here's the star. Here's our sun. It's moving along this elliptical orbit. And again, this elliptical orbit is much more pronounced than the real orbit is, but this is for demonstration purposes. Okay, now let's say in the period of time of 1 month. We could go 1 week, 1 day. We're defining a certain period of time. So let's say in 1 month that planet moves from this location to, say, this location. Okay? That means that in that period of 1 month, it will have swept, or in a sense covered, an area like this. It will have swept across this area. Okay, within 1 month. What Kepler's second law is saying is that, therefore, for any other 1 month period, let's say we're going from here to here, right? Then this planet is going to sweep out an equal area. So you'll notice we're closer to the sun, where I've drawn this here. We're closer to the sun, so these lines have to be shorter, which means in order for the 2 areas to be the same, this distance between the 2 planets has to be bigger. Can you see how this is generally a smaller, or at least a skinnier triangle than this one? Well, they have to have the same area. This is what Kepler's second law says. They're going to have the same area, which means this distance has to be bigger so that you can create this same area, this area that matches the original area, the first one. Okay? And so what we're really driving at here is that at this point, the planet is actually moving faster. At this point, it's moving slower, right? And then if we get as close as we can to the sun, let's say right here, now we're talking even a bigger distance between the 2 points. And the idea here is each one of these is a 1 month period. So now the 1 month period might look something a little more like this. Again, definitely not drawn to scale because I'm not that good. And all three of these areas have to be the same. So what his law is saying that is in a 1 month period, when we're out here away from the sun, we're going to travel a slower or shorter distance within that 1 month period. As we get closer to the sun, that 1 month period is going to, during that 1 month period, the planet's going to move further. It's actually moving faster out here or closer to the sun. Okay, that's Kepler's second law. Kepler's third law is where we get the equation where we can do some work here. Kepler's third law says that the square of a planet's orbital time period, t, is proportional to the cube of its average orbital radius. All right, there's a lot packed in that statement. Let's break down what that's saying. So it's saying the square of a planet's orbital time period, t. So that means going down here next to my proportionality symbol, I'm saying t squared. Okay. T squared is proportional to the cube of its average orbital radius, which we'll call r. Right? So it's proportional to r cubed. So the period of the planet's orbital time, which is the period, if you square that period, it's proportional to the cube of the average orbital radius. Okay? Since these are proportional, we could create this other statement. We could say t squared divided by r cubed is equal to some constant. So if these two are proportional to each other, then if you divide them, you find that constant of proportionality. Now this seems very obscure, except this is where this gets pretty powerful. This t squared divided by r cubed, if we could find that out, for example, for the planet Earth, then that same constant, the same t squared divided by r cubed, that's going to be the same for every planet in the solar system. And that does become pretty useful. For example, let's look at our worked example D.1. Okay? D.1 says, if the average distance between the sun and the planet Venus is 1.08 times 10 to the 11 meters, calculate the time period of Venus's orbit. And we're going to calculate in Earth days. So at first it seems like an impossible problem. Where we're told the average distance from Venus to the sun is this amount. And we're trying to figure out, well, what does that mean that Venus's orbit is? Well, we can use what we know about Earth to figure that out. So we're going to use this proportionality, this t squared over r cubed. Because that's always the same constant, what we can set up is that I'll stick with purple. The orbital period of Earth, so we'll say TE squared, divided by Earth's average distance from the sun, cubed, is equal to the orbital period of Venus squared, divided by Venus's average distance from the sun, cubed. So we can relate one planet to the next using Kepler's third law. That's what makes this pretty cool, something pretty powerful. So let's see what we can figure out. We're trying to get an answer in Earth days. So we're going to start with Earth. That's our left side here. We're going to say the orbital period of Earth. Well, Earth takes 365.25 days to orbit the sun. Remember that 0.25 because that's why we have leap year. So we have 365.25 days. That's the orbital period of Earth. And we're going to square that. So what I'm doing is I'm filling in this right here. That's divided by, well, my handwriting is really bad. I'll see if I can clean that up. This R represents Earth's average distance from the sun. And I added this to our worked example right here. So that distance is 1.50 times 10 to the 11. So 1.50 times 10 to the 11 meters, and that's cubed. That is equal to Venus's orbital period squared, right? And that's what we're trying to find, right? We're trying to find the time period of Venus's orbit. So that's what we're actually trying to solve for. divided by, and then the problem told us what Venus's average distance from the sun is 1.08 times 10 to the 11 meters. So 1.08 times 10 to the 11 meters, and that's cubed. So then we've got only one unknown in our expression here, which means we can solve for it. So I'm going to try that in your calculator. Do that while I'm doing the same thing. See if you can figure out what t is. Don't forget that TV. Don't forget that TV is squared. So ultimately, you're going to need to take a square root to get that. Okay. So what I'm going to enter is 365.25 squared divided by 1.50 times 10 to the 11th cubed, and then that quantity will be multiplied by 1.08 times 10 to the 11 cubed, and we'll get an answer, and then we need to take the square root of that answer, and we get 223.1459296, or we'll say the orbital, whoops, stick with purple here, the orbital time period of Venus is equal to 223 Earth days. Equal to 223 days, Earth days, which we'd expect it would be shorter than Earth because it's closer to the sun. Okay, that's Kepler's laws of planetary motion. Come see me during class if you have any questions, and I'll talk to you soon.